Morning. Can you hear me?
Yes, Maíra, good morning.
Good morning, Damien. How are you?
I'm fine, and you?
Well, fine as well. Thank you.
Just to say hello.
Hi, Demi. How are you? And Urian and Joseph, can you hear me? Let me know when I should start, please. Nuria, you are mute.
Yes, you can start, Maíra.
Okay.
Go ahead. Thank you.
Yeah, thanks. So I'm going to share my screen. And I hope you all can see my screen and my mouse.
Yes.
Yes.
Yeah? All right. So good morning, everybody. First of all, welcome. I apologize that I'm online presenting this lecture, but as you all have experienced, the pandemic has delayed all our travels and meetings. Thank you for the organizers, especially to Joseph, to put this course together and to being so resilient, keeping it for, after all these issues with the pandemic. I'm Maíra Aguiar. I am the group leader of Mathematical and Theoretical Biology in the Basque Country, Basque Center of Applied Mathematics. And my mini course would be on mathematical models in epidemiology. This is quite catchy at this moment, since we are living in a pandemic. And the idea is to give you a bit of information on how to use these mathematical models in real life problems. So just to remember, we have 3 lectures, one today, one tomorrow, and the last one would be on Thursday. The first lecture is quite theoretical, although I'm not there in the blackboard. I hope to have some time to let you to play a bit with the equations. It's mostly focused on some concepts on mathematical epidemiology. The following 2 lectures would be applied, all the concepts we have discussed today, for 2 infectious diseases which are major problems worldwide. One is dengue fever epidemiology, which is a vector-borne disease affecting mostly the tropical countries, and is really a huge burden, social and economical, in terms of public health. And the third one is, of course, COVID-19, that I'm sure that all of you are already a bit of expert on that, but would be quite fun to apply the concepts mostly on the mathematical point of view that we have learned from dengue models. So the lecture outline today would start with a brief introduction, where I'm going to describe or to show you some basic concepts on epidemiology and epidemiological models. We start evaluating and analyzing a most simple version of epidemic models called the SIS model. We're going to calculate the stationary states and the time-dependent solution. So this is a toy model. We can do everything analytically. And I open a bracket here to say that I'm not sure the level of all the attendees of this course. So if you are very fit on the analytics, please don't worry. Next lecture, we are going to have a lot of fun applying those concepts. And in case you do not, you are not very fit on that and you are not able to follow all the analytics, please feel free to contact me in person after this lecture so we can discuss what are the issues. So after the SIS epidemic models, we are going to evaluate the SIR epidemic model. Similarly, looking at the stability analysis, looking at the bifurcation diagrams and the state space plot to see what are the attractors we can get in this model. We extend a little bit to see how this stability analysis goes for higher dimensional models, because the SHAR model. We are looking at the next generation matrix to look at the what we call basic reproduction number and the stability of the system. We increase complexity by adding external force such as seasonality into the basic SIR model, towards which gives us a very rich dynamical behavior, including chaotic dynamics. And if I still have time today, but if I don't worry, tomorrow we can just continue. I'm going to give a bit of introduction on stochastic processes and the mean field approximation that we can use to solve those systems. Okay, so we start giving a brief of introduction about infectious disease dynamics. We all know that infectious disease are the second leading cause of death worldwide, according to the World Health Organization, especially in low-income countries. So we have here in these figures 4 different epidemics. The first one is the Black Death that happened in the 14th century. This one here is about the flu pandemic in 1918. This is Ebola, and this is the COVID. Before we start describing the epidemics using mathematical models, we need to clarify some concepts. What are the difference between endemic, epidemic, and pandemic? So this graphic here shows the difference between an endemic scenario and an epidemic scenario. And while an endemic scenario is the baseline level of disease in a specific geographic area, so it's restricted to that geographic area where the disease is always occurring, an epidemic refers to the number, the sudden increase of number of cases of a particular disease, which is not at its natural endemic state. When these epidemics start to occur in several different areas around the globe, we call it as a pandemic. And the World Health Organization has a definition of it. It's where the disease is new and is growing exponentially in different areas of the world at the same time. So here in this map here, we can see clearly the difference between an endemic, that we see that infectious disease is present constantly over the year in specific regions of the world. An epidemic, when the number of a given infectious disease increases suddenly and then it's controlled. And a pandemic, when this infectious disease is having several outbreaks in different areas of the world. So a pandemic that we are living now cuts across international boundaries. So it's not only restricted to one location, but it goes in many different countries around the world. So this is to illustrate the past pandemics we have lived on. We all find COVID-19 very difficult and very dangerous, but along the human history, we have been through several different pandemics, including the Black Death that has killed more than 200 million people in the 14th century. And we tend not to remember, but the HIV is also a pandemic we are living in nowadays. Regarding COVID pandemic, this is an updated from end of August. We have so far notified more than 200 million cases with 4.5 million deaths, which gives us a mortality, a case fatality ratio of approximately 2%. Well, that's very severe compared to the case fatality ratio of influenza, for example, that is 0.1%. However, it's not as bad as a Black Death. So, of course, we should be careful with that. We have now vaccines and palliative treatments to control and to avoid disease. It is a very bad situation, but it's not as bad as other pandemics we have gone through already. And this is an illustration of the epidemic of the COVID-19 in the Basque Country. We have shown here the data from the beginning of the pandemic in March 2020 to June 2021, where we plot here the number of confirmed cases by testing, PCR or antigenic tests, the number of hospitalizations in red, the number of ICU admission cases in purple, and the number of deceased in black. We have the so-called waves. We have the first wave that was very bad, because first we didn't know about the disease and we didn't know how to deal with that. Seeing here that the number of hospitalizations, ICU disease are mostly basically all of the cases which were detected. And as the testing capacity increased, we were able to find more asymptomatic or mild diseases. And of course, the number of severe cases became low in comparison to the first wave over the period. During the pandemic, the Basque government has put together an initiative to create the Basque Modeling Task Force. And from this Basque model, for this task force, we have, together with other groups in BCAM, developed a mathematical model able to describe the dynamics of the disease and to predict the the number of cases in the next few days. Also, the number of hospitalized, the number of ICU admission cases, and the number of the deceased. This information was very important for the public health managers in order to be prepared for the upcoming days during the pandemic. So the model here looks quite complicated, but it's very, very easy. And we are going to discuss that in the third lecture. Just for you to give a flavor, what we do here is basically to divide the population into susceptible individuals, infected individuals that can be either hospitalized or asymptomatic and mild, and recovered individuals. As individuals who are becoming more severely ill and being transferred to ICU's facilities, we also include this class here for counting the number of ICU patients to be admitted during the pandemic. The C classes here are only counting the cumulative new cases, so basically the incidences, and the deceased class to show how many deceased cases we would expect over the time. This is a type of output that this model gives to us. I'm not sure if you can see very well, but we have the description of the hospitalized, ICU admissions, and deceased over the time. And this Charu-CD modeling framework was giving predictions to the Basque government to prediction of 20 days with weekly reports with the predicted daily incidences. So as the pandemic, the COVID-19 pandemic has progressed, research in mathematical model became imperative and very influential. We were always there, but now became very, very important to know a little bit how to develop these models and how to interpret the results of these models in order to understand the dynamics of the disease spreading and the impact of the control measures such as lockdown and vaccination over time. Okay, so mathematical models have been used in public health, since a long time ago. It helps the health workers to assess the impact not only on the control strategy, but also to decide what are the next decision making to control this pandemic and to help the population to go through this public health problem. This is a very easy way to visualize an epidemic model where we use the so-called state flow diagram with the boxes representing the states related to the disease. In this case here, for example, we divide the population into susceptible and infected. The arrows are the transition rate between one class to another. And we can incorporate different aspects of the disease, making it more complex as we learn about the disease, as we have data to validate those models. And we can end up with a very complicated model, giving a rich dynamical behavior, even in the basic SIR type model, by only adding some external force such as seasonality, for example. So this example here, SIS model, is the most easy and toy model to study. We can do everything analytically, and that's what we are going to do at this moment. Just to recap, we have a population divided into susceptible and infected. Susceptible individuals become infected with an infection rate beta, and wane the immunity, so it becomes susceptible again after a period of time. And we have a constraint of constant population size, and this loop goes on and on and on. For the SIR model, we have an extra class for the recovered, where susceptible become infected with an infected rate beta, recovers with a recovery rate gamma, and after a while, the wane immunity alpha puts these individuals again to the susceptible class. We can model it in its deterministic or stochastic approach. Those are the most common approach in modeling. And the deterministic system is the most used and the most easier way to evaluate those systems, since there is no randomness involved. So we know we know completely the transitions from one state to another without major issues. However, the stochastic systems are very difficult to solve explicitly. Only few stochastic processes can be solved explicitly. We have random presence, and the variable states are then described by probability distributions. Lucky us is that in certain parameter regions, we can use the mean field approximation that give us a closed ordinary differential equation system. And at the end of this lecture, we are going to see how does that work. Okay, so we start with the deterministic SIS epidemic model. As I described to you before, we can also write it down in terms of reaction scheme, and from this reaction scheme, you can get the ODE system. Again, we have a constraint of constant population size, so we say that the total population N is simply number of susceptible, but plus number of infected. And we have for the susceptible class a loss term here, where the susceptible become infected with infection rate beta IS. And this susceptible and this recovered become, and this infected will then recover, becoming susceptible again with a recovery rate gamma. We can calculate the stationary state simply by setting this ordinary differential equation to 0. And assuming that its population size is constant, we end up with a one-dimensional system, very easy to treat. And we can see this in terms of output, depending on the value of the transmission rate you use and the value of the recovery rate you use. The simulation is given by this graph in the left-hand side. So here as an example, I have fixed the population size equal 100. I started with 1 infected individuals and the rest susceptible, and I fixed the recovery rate gamma equals 1. I assume that the number of infected are 2.5 times larger than the number of recovered, which means that I have more individuals becoming infected than recovering in this population. And over time, we see that the number of infected individuals goes up exponentially and end up in an endemic state. Of course, that is dependent or is in function of this infection rate parameter to be larger or smaller the recovery rate gamma. And if you have the infected rate smaller than the recovery rate, so if you have more individuals becoming infected than individuals recovering, you always end up in an endemic state. However, when you have the number of infected smaller than the number of the recovered, the disease will go to get extinct. And the values here will vary according to the value of the transmission rate you use. So if you have any question, please feel free to raise your hand, or maybe not raise your hand, I cannot see it, but open up the mic and let me know, okay? Good. So as I said, to calculate the stationary state, we simply have to set this ordinary differential equation to 0. And it's a very simple expression to be solved. And we end up with 2 different disease equilibrium. The first one is the easiest one, the so-called disease-free equilibrium, where we define that the infected are equal 0. And if infected are equal 0, knowing that N is equal I plus S, we end up with all the susceptible individuals in the population. However, for the stationary state of the disease endemic equilibrium, we have to solve the second part of the equation. And we find out that the number of infected in its endemic state would be given by this expression here. And by setting N equals I plus S, we end up with the number of susceptible in this, this expression here. That is a very simple calculation. We are going to do that together, or I'm going to give you some time to do it for the a bit more complicated model, but it's also very easy to do. Okay, summarizing, for the simple SIS model, we have 2 disease equilibrium. The first one is the trivial one, the disease-free equilibrium, where we have no infected and all the population are susceptible. And the endemic equilibrium, where we have a given endemic number of infected and susceptible. So here's a simulation to show again the population size is 100. I start here now with 20 infected individuals. I fix the recovery rate equals 1 without any loss of generality. And what we can see here is that by varying the transmission rate below or above the recovery rate, the dynamics change. When it is below, it goes to extinction faster or slower, depending on the value of beta. or it goes to the endemic state faster or slower than according to the value of beta. So that will reflect the number of the endemic number of infected individuals in that population we have. Here, just to illustrate in log-log plot, we have the extinction of the disease for beta values below gamma, endemic state for beta values above gamma, and we have here power law that we are going to discuss. That is when the value of beta is equal to the value of gamma, what we call critical value in the epidemic model. So to do the stability analysis, we simply call this dynamics as function of I. And we have to define that delta t is equal this expression here. We do a small perturbation away from this fixed point, and we can solve this ordinary differential equation very easily as well. We linearize via Taylor expansion, and this is the first exercise to you to do. It's a bit of calculation, but it's very simple to do, where we end up with a linearized differential equation. So from this linearized differential equation, we simply have to insert for this I star the respective stationary state that we have calculated, either for a disease-free equilibrium and or for the disease endemic equilibrium. And then with that, we do the so-called local stability analysis. So for the disease-free equilibrium, we have to solve this equation here, and we simplify delta t, we simply call by x, where we have to insert for disease-free equilibrium 0 for I. And we end up with this expression here, where we can identify the stability of the system on the disease-free equilibrium. So when we have the number of infected being larger than the number of the recovered, we have a positive exponent, which means that the fixed point is unstable. However, for the disease-free equilibrium, when you have more individuals becoming recovered than becoming infected, we have a negative exponent, which means that we have a stable fixed point. We are going to see that in the bifurcation diagram soon. The second equilibrium is the so-called disease endemic equilibrium. We do the same calculations, but now we insert for the infected this expression here. Again, another exercise for you to do. And we end up with this expression here that similarly than the one I have shown for the disease-free equilibrium, we can evaluate the stationary state. So when we have the number of individuals becoming higher than the number of recovered individuals, we have a negative exponent, which means that for disease endemic equilibrium, we have a stability for beta larger than gamma. And in the other hand, for beta smaller than gamma, we have a positive exponent, which gives that instability of the system in this region. Okay, so this is only to summarize what we have done. For the disease-free equilibrium, we have calculated this expression to evaluate the stability of the system. For the disease endemic equilibrium, this one. And we see that for beta below gamma, smaller gamma, so beta smaller than 1, because my gamma is fixed to 1, as you remember, we have stability. And when beta becomes larger than gamma, this region here becomes unstable. So you no longer get the disease-free equilibrium. Any time, any moment you start in this parameter region here, you are going either to the second stationary state rather than the first one. On the other hand, for the disease endemic equilibrium, you have stability for beta larger than gamma and instability for beta smaller than gamma. And in our case, beta smaller than gamma is not even biological because we do not have negative infection, so we don't worry about this part here. Okay, so in terms of simulation, we can vary the value of transmission rate smaller or larger than gamma. And we see that for all beta values below 1, the system always goes to extinction. It is stable going to extinction. And that takes longer or it goes faster according to the beta value you choose. On the other hand, if you choose beta to be larger than gamma, we see that the system starts growing towards its endemic state, and the final number of infected would be larger or smaller depending on the value of beta. What we see here in this bifurcation diagram, that the system changes stability when beta is equal gamma, and that's what we call the critical point in the epidemic system, epidemic model. As I said, this system is very easy to solve, and this is another exercise for you to do. We can have the complete time-dependent solution by solving simply this equation here, and the final result is really trivial, where we have the endemic states of the infected here over this mumbo jumbo. And by changing the value of beta, you go either to extinction or to the endemic state, with the system changes stability with a power law behavior for assuming beta equals gamma. So, and this time-dependent solution here can be used to verify all the three different behaviors we have discussed. So the disease endemic equilibrium, the disease-free equilibrium, and the epidemic threshold, the so-called epidemic threshold, where we have this power law coming out. So the illustration of the disease-free equilibrium. So we have the solution of the this equation here, and we have the time-dependent solution on top. That's seen that is a very good agreement. And for the disease endemic equilibrium as well, the only difference here that I start with a different time t, but it goes always towards the endemic states. At the epidemic threshold, we have a very special situation, and it can be found when we set that the both number, so when we set that the transmission rate is equal to the recovery rate, so you have the same number of individuals become infected and recovered. So we simply assume that beta is equal gamma, and the equation to be solved is this one here. And the time-dependent solution is much simplified, giving a power law, which in log-log plot shows a straight line. So far, so good? I will assume yes. If not, please let me know. So you see that we have been able to do everything analytically in the simple model, but life is more complicated than the simple SIS model. And we have then to add a bit more of complexity into the system in order to understand real life problems. So the second and very well-known epidemic model is the SIR model, where it applies to infectious diseases where people become infected, lose this immunity, and then become susceptible again. So similarly to the SIS, we have an extra class here, susceptible, infected, and recovered. We can write down the transitions or the dynamics of the system using the reaction scheme. And the notation used here is the number of susceptible at time t, number of infected at time t, number of recovered at time t. N is my total population size with the constraint of N, the constant population size. So N is equal I plus I, S plus I plus R. And we have these three parameters here for the transition: the infection rate, the recovery rate, and the waning immunity rate. I would give you 5 minutes eventually to write down the ODE system to see if we can get the same equations. Is that okay? No interaction? So weird. Nuria, is that okay if I give 5 minutes to the participants to calculate a little bit? Hello,
Yes.
Are you there?
Yeah.
Yeah, I mean, so weird. I'm sorry for this not really presential course, but I hope that you are being able to follow. So I give you 5 minutes to calculate to write down the equations for the SIR model. And I leave you here with the assumptions of the model. Again, we have a total number of total constant population size. So the N population would be composed by infected, susceptible, and recovered. We do not assume death due to the disease. So we have no demography. Of course, this is an extra thing to add into the models. We assume homogeneously mixing population, which means that every infected individual will transmit the disease equally to the susceptible individual. So there is no difference in transmissibility. So there is no heterogeneity into this population in terms of transmission or susceptibility. Similar to the SIS, susceptible individuals get infected and infective at rate beta. Infected individuals will recover at rate gamma and will develop immunity against this disease. And then after a period of waning immunity, this recovered individual becomes susceptible again. So we have always a loop on the disease-related stages in this population. So I give you 5 minutes just to write down the equations. I can give leave the reaction scheme here. To see if we end up with the same equation system. If the first one to finish, just say finished so I can move forward.
Finished? Yes, we're finished.
That was fast. All right. So this is my ODE system. So we have an ordinary differential equation for the susceptible individuals and the ordinary differential equation for the infected individuals, assuming that the recovered are simple the number of the population minus the susceptible minus the infected. So in the susceptible class, we have a loss term here. So the susceptible become infected with infection rate beta over NIS, and the infected individuals become recovered with a recovery rate gamma. And after a waning immunity period alpha, those individuals become susceptible again. So we have beta over NIS as a ratio of the rate of infection caused by susceptible individuals meeting infected individuals and then become infected. We have gamma I from the infected individuals becoming recovered, and we have alpha R, the rate of recovered individuals re-entering into the susceptible class. So we can give, using Euler scheme below here, the solution of this ODE system that will show the variation of the number of susceptible and the number of infected in this population. As we have shown for the SIS model, this SIR model has also two possible steady states, the so-called trivial disease-free equilibrium, where there is no infected in the population, and that's we all aim, especially now with in the case of COVID, or the disease endemic equilibrium, when the number of susceptible infected reach an endemic, so a constant number in that population. And that's, unfortunately, that's what we are going to expect for COVID-19 in the next few months or so. So we can solve this two equations here as an exercise 5. And again, according to the SIS that we have done everything explicitly, we only have fixed point here for the SIS, for the SIR system, where for the disease-free equilibrium, we have 0 infected and everybody susceptible. I start here with transmission rate being below the recovery rate. Again, when we have beta smaller than gamma, we have always the dynamics going toward extinction, so the disease is controlled when we have more people recovering than being infected. My starting point here is 40. It was not very nice. I should have started below here, that we would say we would see an increase of number of infected and then going extinct. And this is the dynamic for the recovered individual and for the susceptible individual. According to the beta value you choose, this dynamics goes faster or slower, but always to the extinction when we have beta below gamma. For the disease endemic equilibrium as well, so you see, you can remember here that you have the similar stationary state for the endemic equilibrium for the SIS, plus this mumbo jumbo here for the waning immunity. And the susceptible is given by setting n equals I plus S plus R. And similar to SIS, again, we have the same behavior of number of infected increasing for beta larger than gamma, and then going down towards endemicity. And the number of infected here in the SIR is much smaller than the number of in the SIS, independent of the value of beta being larger than gamma. The dynamics are pretty much the same. The difference that for the SIS, we have immediately going up an endemic state without any oscillations. For the SIR, we have already a bit more of complicated dynamics with some oscillations towards the endemic state. The stability analysis is done exactly the same. So we do the linearization via the Taylor expansion. We obtain a linear differential equation system. We can write down the Jacobian matrix. We can do the eigenvalue decomposition and the local stability analysis. In summary, for these two disease equilibrium, we have to evaluate the stability of the system. So for the disease-free equilibrium, we have stability when the number of infected are smaller than the number of recovered. We have instability when the number of infected is larger than the number of recovered, and the system also changes stability when the number of infected is equal to the number of individuals being recovered. For the disease endemic equilibrium is the other way around. We have stability when individuals are getting, when the number of infected individuals are larger than the number of recovered individuals, and it becomes unstable when the number of infected individuals are smaller than the number of recovered individuals. For this endemic equilibrium here, we have already complex eigenvalues, which is going to give the frequency of the oscillations toward the stable, toward the endemic state. And that's what we are going to see now. Okay, so in order to analyze the stability of the equilibrium states, endemic and free equilibrium, we look at the Jacobian matrix and its eigenvalues. So the SIS, we are looking only at the exponential of the expression we have calculated. Now we have a two-dimensional system, so we look at the eigenvalues of a matrix. For the eigenvalues, we know that when eigenvalues are negative, we have stability, and when one of the eigenvalues become positive, the system becomes unstable. And we look at each one of the endemic states, given what disease equilibrium we have calculated. So we can write down, we can solve the Taylor expansion around this fixed point, and we get the linear differential equation system shown here. This is also an exercise for you to do. It's a very good fun. It's important for us to understand when we look at more complicated systems, to understand what is the background information we have in terms of mathematics. We can write down the Jacobian matrix where we insert the disease equilibrium in this for the infected individuals. We call this matrix as A, and then we can calculate the eigenvalue and the eigenvalue decomposition by using this expression here. And the eigenvalues will be calculated by setting the determinant of this expression to 0. This is all trivial calculations. We all can do that. But again, if you have any problems with the analytics, please feel free to contact me. We can do it together. Okay, so let's analyze the behavior of the system, of the SIR system at both disease equilibrium. The first one is the easiest one, the disease-free equilibrium, where we have to insert for I and S the 0 and N result from our stationary state. And the eigenvalues are simply given by these two expressions here. The output is very clear, where we see that eigenvalue, the first eigenvalue, it's always negative. And the second eigenvalue for the disease endemic equilibrium would be negative till it reach the critical point of beta equals gamma. So for this region here, for beta between 0 and 1, we have a stability of the disease-free equilibrium with both eigenvalues being negative. Two eigenvalues cross when beta the two eigenvalues have crossed at beta value 0.9, because you simply need to set this eigenvalue here to equal to 0, and the system changes stability when beta is equal gamma. When system changes stability, the disease-free equilibrium becomes unstable with a positive eigenvalue dominating the dynamics, and you no longer have stability for the disease endemic equilibrium when beta is larger than 1. On the other hand, so let me just show here the simulation. So the fixed point for would be stable when the eigenvalues are negative and unstable when at least one the eigenvalues are positive. So this for the disease endemic equilibrium, we have these dynamics always going to extinction depending on the value of beta you have. For the disease endemic equilibrium, we have both negative eigenvalues for beta larger than 1, which gives the stability of the system change. It's unstable, and as soon as the eigenvalue, one of the eigenvalues become positive, we have a stability for the disease endemic equilibrium. Let's see here. For the infected, here I start with 40 infected in the population. It goes a bit up and then goes down towards endemic states with a bit of oscillations. And as we have shown here, the stability of the system changes when one eigenvalue becomes 0, which means that we have a transcriptical bifurcation. I guess the next lectures we are going to have more information on the type of bifurcation we can find in these systems. So you see that the bifurcation diagram here is pretty similar to the one obtained for the SIS model. The only difference is relying on these oscillations that we have towards the endemic state. So we can calculate the corresponding eigenvalue using this expression here. And for the first eigenvalue, lambda 1, the eigenvector is given by this expression here. And for the second eigenvalue, we have the eigenvector given by this simple matrix here. We can evaluate the eigenvectors for both equilibrium. The disease-free equilibrium in function of the transmission rate is the following. So we have set the eigenvector for the first eigenvalue and the second eigenvalue here. And in red, we have the dynamics always going towards extinction. So you see here that my beta value is below gamma, and I would expect to have extinction after a period of time. As we get close to the criticality, the dynamic still goes to the extinction. However, one of the eigenvalues changes, and this dynamics toward the extinction become slower and slower up to reaching the critical point, where even though you have one eigenvalue forcing towards the extinction, the largest eigenvector is going always to send back the dynamics towards the endemic state. So it becomes unstable when beta becomes larger than gamma. And here we can observe faster and faster the dynamic going away from the fixed point of the disease-free equilibrium. And that's what happens, the change of the stability. So here we have stable because it is below gamma, and here we have unstable because it's above gamma. The same thing we can do for the endemic equilibrium. Is a more complicated calculation to do, but we end up with some simplifications here. We call these terms as A and B, and we can evaluate the eigenvalues such as described here, such as shown here. And when we assume that this B eigenvalue is real, the real part of the eigenvalue would give the contraction towards the fixed point. And if B is below 0, is smaller than 0, the eigenvalue will become complex, where we have the real part giving the contraction or expansion towards the fixed point, and the imaginary part will give the frequency of the oscillations towards the endemic state. That's the spiraling to the fixed point of the endemic disease. So we can see here in terms of bifurcation diagram varying beta, we have for the disease endemic equilibrium, both eigenvalues 1 and 2. When we have beta below gamma, we have one eigenvalue positive, which gives instability of the system. Sorry, I forgot to put the dashed line here and where the system changes stability. The system changes stability when one eigenvalue reaches 0. And when beta is larger than 1, we have already both negative eigenvalues giving the stability of the system for the disease endemic equilibrium. So what I have here in the right-hand side is plotted the real part, A, of the eigenvalues given the contraction towards the endemic state. And for beta, smaller than gamma, the fixed point is unstable. So we have a positive eigenvalue here. The system changes stability when the first eigenvalue reaches 0. And the straight line here is only showing the real part of the complex eigenvalue that is giving the oscillations toward the fixed point on the endemic equilibrium. So here in the left-hand side, I plot the imaginary part of the eigenvalues given the frequency of the oscillations towards the endemic equilibrium. So we can calculate the corresponding eigenvectors of the disease endemic equilibrium. For the first eigenvector, we can, so the eigenvector, for the first eigenvalue, the eigenvector is given by this expression here. And similarly, for the second eigenvalue, we have the eigenvector given by this expression here. And to illustrate, we can see how it behaves at the disease endemic equilibrium state in function of the infection rate parameter. So see here that we have beta larger than gamma. My gamma is always fixed to 1. We see the eigendirection 1 and 2, and we have the trajectory of the system that it is really close to criticality. So the tendency of the dynamic is to go towards extinction, but at some point it just moves back to the endemic state. And as we increase beta, these dynamics are going to the endemic states faster and faster until it is spiraling into the fixed point. So that's given by this frequency of the imaginary part of the eigenvalues. Okay, so just to summarize what we have done in terms of stationary stability analysis for the SIR model, we cannot calculate the time-dependent solution explicitly. So that's why we have done this for the SIS model. Although the behavior of the SIR model is pretty similar to the SIS model, we have this extra feature here of the oscillations that would resemble waves of epidemics towards its endemic state. So in terms of dynamics in function of the transmission rate parameter beta, we have the spreading of the disease when the number of infected is larger than the number of recovered individuals. So you have an oscillation towards the endemic state. However, when we have more individuals becoming recovered than becoming infected, we have the solution of extinction of the disease faster or smaller according to the beta value you choose or you define to your epidemic system. And that basically describes what we all have been exposed since the pandemic start, the basic reproduction number, that in the case of the SIR model is simply the ratio between the number of infected over the number of recovered individuals. And we know that when we have a basic reproduction number smaller than 1, the infection will die out soon or later, depending on the value of beta. However, when we have the basic reproduction ratio, basic reproduction number larger than 1, the infection will be able to spread in the population. Okay, so let's go back to some basic concepts in epidemiology. What is the definition of a basic reproduction number that we have been all exposed in the past 18 months or more? So the basic reproduction number is simply a number of secondary cases generated by a primary case, by an index case, in a population where there is no immunity. So a population should be completely naive, and the first index case will generate new cases. These new cases would be the so-called basic reproduction number. And we can calculate it basically dividing the number of secondary cases generated by this index case over this index case. Okay, so let's do that for the SIR model, where we assume that the number of susceptible is approximately the number of the whole population, so there is no immunity. And we can solve the decay of the primary cases very simply with this equation here, given this solution as we have for the SIS model. And we can look at the exponential to see what would be the basic reproduction ratio we are going to obtain. So we solve also the equation for the number of secondary cases that were generated by the primary cases, and the result is this one here. And with assuming that time goes to infinity, we end up with this solution where these terms here cancels out, and we end up with a beta over gamma as a basic reproduction ratio, for the completely susceptible population. And these solutions here can be generalized then for a more complicated system. Just to illustrate, the average number of individuals, so from an index case generating new cases, which is going to resemble the basic reproduction number we all started hearing about in the beginning of 2020, saying that COVID had a basic reproduction number of, I don't know, 5 or 6 or 7, also the Delta variant. This concept can be only used when we have a completely susceptible population. That's no longer the case for COVID anymore. Each disease has its own basic reproduction number, and this is the variation, for example, COVID-19, that nowadays was it's said to be something between 2 to 2.5. The basic reproduction ratio, the basic reproduction number, sorry, is to be between 2 to 2.5. That means that a single infected individuals in a completely susceptible population can generate 2.5 new cases of the disease. For the H1N1, so the swine flu, we have between 1.2 and 1.6, and Ebola 1.6 and 1.2. When we look at the childhood disease, such as measles, for example, this basic reproduction number goes very high, up to 15, which means that one single case can generate 15 new secondary cases. Okay, so before I move to a higher dimensional system, is there any question here? No? So we continue.
Yes.
Joseph? Okay, so we continue. As I said, so these solutions here can be generalized to higher dimensional system. The simple SIR model could eventually be used to describe diseases such as influenza, where we have individuals susceptible become infected and recovered, and after 5 or 6 years it becomes susceptible again. But then we have to add another features, because we know that strains there are variants which are more similar than the others. You have some partial immunity, etc., etc. So we always have to add more information as more variables and more parameters as we learn more about the disease. So this is a CHAR model that I have used basically to evaluate the COVID-19 in the Basque Country. This is an extension of the simple SIR model, where my infected class is simply divided in two, where I have severely form of the disease with individuals prone to hospitalizations in this class H, and mild and asymptomatic infections in this class A. It's exactly like the SIR model. The issue here is that the infected class is now divided in two classes for severe and mild disease. Again, we assume that at the beginning of the pandemic, we had basically the whole population susceptible, so there was no immunity. And we obtained this linear ODE system here, where we call H and A matrix like vector X. And for the entries of the disease class, so the primary cases, we have this matrix that we call B, and for the exit, we have this matrix that we call G, just to simplify, given this equation system here to be solved, that has the same format obtained for the SIR model. So where the matrix B represents the entries for the infected, and the matrix G, the exit for the recovered. Okay, so for the primary cases, so the index case of hospitalized and asymptomatic or mild, we have this expression here given this solution. And for the secondary cases generated by the primary case, we have this expression here given this solution. And in theory, we can calculate the basic reproduction number by this expression here. However, we do not do that, What we do is basically, by assuming that time goes to infinity, we can write down the generate matrix such as described here. And from generation to generation, the discrete interaction is given by this expression here. And from that one, we look at the dominant eigenvalue in order to say if the system is in stability or instability in terms of the disease-free equilibrium. Okay, so if we have the dominant eigenvalue being smaller than 1, we have stability, and which is larger than 1, we have instability at the disease endemic equilibrium. So we end up, after all this mumbo jumbo, with two measurements that we can use during an epidemic or in the pandemic. We have the basic reproduction number, which is no longer a basic reproduction number because at this moment we have no, so the population is not completely susceptible. So we call that the momentary reproduction number that we calculate by assuming a certain part of the population susceptible, but not all of them. And we have the term here, beta over gamma, so the number of infected over the number of recovered. And we have the growth rates, lambda, that can give, that will and should give the similar result that's observed for the momentary reproduction rate. So this is an example for the Basque Country at the beginning of the pandemic. So this is beginning of March 2020 towards April 2021. Sorry, there was a typo here. And we see that we started with a very high momentary reproduction ratio that went down. And in the middle of April 2020, it crossed the epidemic threshold of 1, which means that it was controlled at this time after the lockdown and was kept under control till middle of 2021. We can observe the growth rates for each one of the variables we have in the case of shadow CD model that I presented to you. For number of positive in yellow, number of hospitalizations and number of ICU admissions, that they follow pretty much the same sigmoidal shape, crossing the epidemic threshold at the same point as we observe for the momentary reproduction ratio. So both measures can resemble or can give us some insights on how the epidemic is going. It's spreading or being controlled. And that we are going to discuss in detail in the next lecture when we apply these concepts we are discussing now. Okay, so, but it can become more complicated. And we all know that especially for respiratory diseases, they have a seasonal behavior. So when you are in the winter, you have more transmission than in the summer. And that's what we do here. We simply add a seasonal force into the system in order to see which kind of output it gets. So again, here we have the basic SIR model. The susceptible individual become infected with infection rate beta, which is now time dependent. So we simply add a cosine function here, and infected individuals become recovered with a recovery rate gamma and become then susceptible after waning immunity. We can write down the equations, it's the same. The only difference here again is that the transmission rate is time dependent. We simply plug in a cosine function, and the behavior in terms of times is completely different than the one we have observed for the non-seasonal model. I'm going back quickly just to show you, to remind you. So this is the behavior we get. So we have one wave and we go to stationarity. And as soon as we add a seasonal force into the system, we see here these oscillations coming every 3 to 5 years. And over time, we can evaluate in terms of state space, and we see that the maximum of each one of the peaks are never the same. So you have a regular behavior. And because you have a larger dimensional system, we no longer look at the eigenvalues, but we look at the Lyapunov exponents. I'm sorry, just a blank here. And in this case here, for the seasonal SIR that we use to evaluate the dynamics of influenza, we have a positive Lyapunov exponent, which is a fingerprint of the so-called deterministic chaotic behavior. So what are the characteristics? What is the definition of deterministic chaos? So we need at least three-dimensional system. In this case here, we have susceptible, infected, and the seasonality. And then when we look at it, we see irregularity in the outbreaks as opposed to the SIR model that I have just shown to you. And the chaotic behavior is defined by having a short term of predictability. So you have a limitation on the predictability of the system and a long-term unpredictability. And we are going to see that in the lecture tomorrow. Just keep on eye in the time, so we still have some time. Okay, so for the seasonal SIR model, we can vary the seasonality and we can plot the bifurcation diagram, and we see that we have a super rich dynamic behavior. So for the non-seasonal SIR, we only have fixed point. As soon as we add seasonality, we have fixed point. We can find limit cycle, more complicated limit cycle. Here, it's so-called torus bifurcation that I guess you are going to be exposed in the next lecture, and the so-called chaotic attractor. And all of these bifurcation points can be defined by calculating the so-called Lyapunov exponents. And we are going to see that in detail in the lecture tomorrow. Okay. So, and then of course, as I said, we can make it more complicated. We can add more classes. We can add more parameters, always with the attention that the models must be validated. It's very nice to have a very complicated model, but if you do not know what we are looking at, if you cannot validate with the empirical data we have, the models are useless. So please, if you want to play with that, be sure to have a good data to evaluate your proposed model. Okay, so we have done all in the deterministic approach, but most of the diseases or the real life problems are stochastic. So as an example, I'm going to describe the stochastic SIR epidemic model that is modeled as a time continuous Markov process to capture this noise on the population. Okay, the dynamics of the probability of infected and susceptible will goes as we defined at the deterministic SIR. However, we have probabilities now for becoming infected or susceptible, and the recovered would follow from the constraint of constant population size, which means that my population N is equal S plus I plus R. And we can write down this as a master equation where we have the gain term of the number of infected, and we have the loss term of the number of infected. So these transition probabilities have, again, one unique absorbing state. So you always go to extinction. And the process is simulated very often using the Gillespie algorithm, which gives the stochastic realizations for the infected individuals and the susceptible individuals over time. So for an example here, for the situation where the number of infected individuals is smaller than the number of recovered individuals, you will start a simulation. But let's look at the infected individuals. Population equals 100. We start with 60 individuals. You have more people being recovered than being infected. All the realizations, and I guess I have 5 realizations here. All realizations goes towards extinction. However, when we have a number of infected larger than the number of recovered, this, although the absorbing state is always the unique state in the system without any extra imported cases, goes to extinction, but it takes longer. Some of the realization goes faster, another takes longer, and we end up with the extinction of the disease, even when we have a number of infected individuals becoming larger than the number of recovered individuals. But what we can do here is for some parameter regions, we can define the mean values of the number of infected and susceptibles. And when we calculate the dynamics by inserting these mean values into the master equation, we end up with this system here, where number of recovered is simply number of the total population minus the number of susceptible minus the number of infected. And what we have to assume here is to neglect cross correlation. So we simply say that S plus I minus S plus I is minus, I'm sorry, So we have a nonlinear transition in the master equation for these higher moments here. And the simplest approximation, that's the so-called mean field approximation, when we assume, when we neglect cross correlation. So we assume that S times I is equal S times I out of the bracket. So there is no variation here. And when we do that, we simply remove this parenthesis here, and we end up with the closed ODE SIR system that we have just calculated in the lecture. Okay, so I have some just comments on the stochastic system. That was really brief, but I wanted to introduce that to you because for the COVID models, we use the stochastic framework for the shadow CD model. It's important to know that for the stochastic simulations, the population size matters. So when we use a finite size population, the extinction phenomenon is going faster or later, depending on the population size you use. That's opposed on the deterministic model that we can get endemic states without any extra cases, such as so-called imported cases. So when we compare the deterministic and the stochastic dynamics, we can observe that the magnitude of the stochastic fluctuation will decrease with the population size you have. And we are going to see that here, for example. So we have here the deterministic simulation for the SIR model in pink. I don't know if you can see it, but it's there. And the stochastic simulations, realizations. Here I have made, I guess I have 20 or so, for a small population size of 1,000 individuals. And as I increase the population size, my deterministic solution goes closer and closer to the mean of the stochastic realizations till we reach the same behavior for a very large population size. So for large enough population size, the stochastic system could be well described by the deterministic skeleton. And we are going to see that in the next lecture, where we really compare the bifurcation diagram for the stochastic system and the deterministic system applied to dengue fever. And by doing that, we gain insight into the relevant parameters to that given problem we are working, basically looking at the topological information of the dynamics we have. Okay. Again, it's very brief and short on the stochastic system, but in the next lectures, we are going to see the application of it to a real life problems. And we know that the mean field approximation is a very good approximation for some of the parameter region we are looking at. It's very difficult to handle stochastic systems analytically, so we need to find either we use numerical simulations or we use the mean field approximation in order to treat the system as a deterministic system. Okay, so I end up here just to show you some real world data we have that we are going to discuss. This is for dengue fever in 2 different regions of Thailand. We see that in the north of Thailand, the epidemics of dengue fever looks like an ODE solution, while that in Bangkok, where we have a much larger population, the epidemics are very noisy. And for that kind of dynamics here, we would need to have the stochastic system simulation in order to describe these dynamics. So when I compare the simulation for the deterministic and the stochastic SIR model, just to see the difference. So in the deterministic, we have this single wave, second wave towards endemicity, and the stochastic population noise just resembles several different waves that we are all exposed by now on COVID. In the case of Basque Country, we are now finishing the 5th wave, and let's see what's going to happen in the next wave. Okay, so I mean, that was a lot. First of all, I would like to thank you for your attention. I hope that you got a bit of flavor of the concepts we are using and how we treat epidemic models, and to apply this in real life problems that will be shown tomorrow and on Thursday. I have 3 references here that you can look at where we talk about the basic models SIR and SIS here. The SHAR model is always, it's already published, and we have calculated the basic reproduction number. And this SHAR model served as an extension or served as a baseline to extend the shadow CD framework that we use to evaluate the behavior of COVID-19 in the Basque Country. And for the basic reproduction ratio and the growth rate, we have this paper here in PLOS that's really very didactical and shows how to calculate those measures. As I said, if you are very good at the analytics, don't get bored. Tomorrow we are going to apply all of these concepts. If you need help with some of the analytics, please feel free to contact me. The organizers have my email address, and it's also very easy to find. Just write down Maíra Aguiar in Google, you might find. For those who are interested in a more long-term courses on epidemic models, we are going to have a mathematical models in epidemiology course in the next spring at BCAM. We also have a conference going on in the next February where we can present your work and discuss and contact with several different researchers around the world. And just to let you know, stay tuned on the Facebook, Twitter, and get to know what our group is, what are the activities of our group at BCAM. Thank you.
Thank you, Maíra.
Yeah, we have 15 minutes in case there is any questions or comment, or if you want to see something in more detail, we still have time. I guess you are all very tired. I am. But it was good to give a kind of an overview of what we have been done in the last 15 years. Where are the faces of people? Let me see your faces. Hey, Nicole.
Hi.
Vicente, Visda, Vanessa, Damien, Sylvia,
Hi.
Carlos, Akil.
Hi.
Hello.
Any questions?
Either you didn't get anything or it was so good that you got everything. Hopefully the second. But as I said, the fun part would come tomorrow, where we are going to apply this to real world problems. I guess all of you are curious on COVID-19. I don't know, is there anybody doing mathematical modeling that can share the experience? How they, which type of model you have used to evaluate? No? Tired? Hope you have enjoyed, hope it was of interest, and we'll be back tomorrow. Giuseppe, I give it over to you. MTB group in mass here. So Nicole, Vista, Akil, Vanessa, Damien, Carlo, all of them are part of the MTB group. And they are going to participate in the course as well. Some of them giving lectures. So if you are interested, please contact us.
Maíra?
Yeah.
No.
Josep?
El tinc obert, Ara és amb mute? Sí. Però... do you have any...
Hello, Maíra, can you hear?
Yeah, it's a bit of echoing, but I can. Who is speaking?
Yes. It's I'm Tomás Alarcón. Hello, how are you? Anyone has any questions for Maíra? No? No. Okay, then. Oh, yeah. They are asking me if it is possible to have these slides.
Yes, sure. I can share these slides, no problem.
So they are asking you to post the. We can help you with this, Maíra. If you send us if you send Nuria or Vanessa the slides, because they would like to have them before the lecture. So if you can, then Vanessa and Nuria can help
All right,
you with.
I will send you during the break. Don't worry.
Good. Thank you.
Yeah, welcome.
So
Guys, relax a bit. I know that was a lot of information. I hope that the next time I will be there in presence and we can do some Blackboard exercise, because it's really more useful than showing the final results. But you have all the exercise and you have access to the slides. You can calculate. And in case of any problems with the analytics, please contact me. I will add my email address into the slides and you can contact me. Okay. Once again, thank you for attending, and thank you for the organizers. See you tomorrow again. I mean, I will be around, but see you tomorrow again with the applications.
Okay, thank you, Maíra.
Thank you.
Bye-bye.
Thank you. Bye.